Welcome to the presentation on simplifying radicals. So let's get started with a little terminology out of the way. You're probably just wondering what a radical is, and I'll let you know. Let's see. Let me get the pen settings right. A radical is just that. Or you're probably more familiar calling that the square root symbol. So with the terminology out of the way, let's actually talk about what it means to simplify a radical. And some people would argue that what we're going to actually be doing is actually making it more complicated, but let's see. Let me erase that. So if I were to give you the square root of 36, you'd say, hey, that's easy. That's just equal to 6 times 6. Or you'd say the square root of 36 is just 6. Now what if I asked you what the square root of 72 is? Well, we know that 72 is 36 times 2, right? So let's write that. Square root of 72 is the same thing as the square root of 36 times 2, right? We just rewrote 72 as 36 times 2. And the square root, if you remember from level 3 exponents, square root is the same thing as something to the 1/2 power. So let's write it that way. And I'm just writing it this way just to show you how this radical simplification works, and that it's really not a new concept. So this is the same thing as 36 times 2 to the 1/2 power. Right? Because it's just a square root is the same thing as 1/2 power. And we learned from the exponent rules that when you multiply two numbers and then you raise that to the 1/2 power, that's the same thing as raising each of the numbers to the 1/2 power and then multiplying them. Right? Well, that right there, that's the same thing as saying square root of 36 times the square root of 2. And we already figured out what the square root of 36 is. It's 6. So that just equals 6 times the square root of 2. And you're probably wondering why I went through this step of changing the radical, the square root symbol, into the 1/2 power. And I did that just to show you that this is just an extension of the exponent rules. It isn't really a new concept, although I guess sometimes it's not so obvious that they are the same concept. So I just wanted to point that out. So let's do another problem. I think as we do more and more problems, these will become a little more obvious. The square root of 50. Well, the square root of 50 is the same thing as 25 times 2. And we know, based on what we just did, and this is really just an exponent rule, the square root of 25 times 2 is the same thing as the square root of 25 times the square root of 2. Well, we know what the square root of 25 is. That's 5. So that just equals 5 times the square root of 2. Now you might be saying, "Hey Sal, well, you make it look easy, but how did you know to split 50 into 25 and 2? Why didn't I say that 50 is equal to the square root of 5 and 10, or that 50 is equal to the square root?" Actually, I think of 1 and 50. I don't know what other factors does 50 have. Well, anyway, I won't go into that right now. Well, the reason why I picked 25 and 2 is because I wanted a factor of 50. I actually wanted the largest factor of 50 that is a perfect square, and that's 25. If I had done 5 and 10, there's really nothing I could have done with it, because neither 5 nor 10 are perfect squares, and same things with 1 and 50. So the way you should think about it, think about the factors of the original number, and figure out if any of those factors are perfect squares. And there's no real mechanical way. You really just have to learn to recognize perfect squares. And you'll get familiar with them. Of course, they're 1, 4, 9, 25, 9, 16, 25, 36, 49, 64, etc. And maybe by doing this module, you'll actually learn to recognize them more readily. But if any of these numbers are a factor of the number under the radical sign, then you'll probably want to factor them out. And then you can take them out of the radical sign like we did up in this problem. Let's do a couple of more. What is 7 times the square root of 27? And when I write the 7 right next to it, that just means times the square root of 27. Well, let's think about what are the factors of 27 and whether any of them are a perfect square. Well, 3 is a factor of 27, but that's not a perfect square. 9 is. So we could say 7, that's equal to 7 times the square root of 9 times 3. And now, we based on the rules we just learned, that's the same thing as 7 times the square root of 9 times the square root of 3. And well, that just equals 7 times 3, right? Because the square root of 9 is 3, times the square root of 3. That equals 21 times the square root of 3. Done. Let's do another one. What is 9 times the square root of 18? Well, once again, what are the factors of 18? Well, we have 6 and 3, 1 and 18. None of the numbers I mentioned so far are perfect squares, but we also have 2 and 9. And 9 is a perfect square. So let's write that. That's equal to 9 times the square root of 2 times 9, which is equal to 9 times the square root of 2, that's a 2, times the square root of 9, which equals 9 times the square root of 2 times 3, right? That's the square root of 9, which equals 27 times the square root of 2. There we go. Hopefully you're starting to get the hang of these problems. Let's do another one. What is 4 times the square root of 25? Well, 25 itself is a perfect square. This is kind of this problem is so easy, it's a bit of a trick problem. 25 itself is a perfect square. The square root is 5, so this is just equal to 4 times 5, which is equal to 20, right? Square root of 25 is 5. Let's do another one. What's 3 times the square root of 29? Well, 29 only has two factors. It's a prime number. It only has the factors 1 and 29. And neither of those numbers are perfect squares. So we really can't simplify this one anymore. So this is already in completely simplified form. Let's do a couple of more. What about 7 times the square root of 320? So let's think about 320. Well, we could actually do it in steps when we have larger numbers like this. I can look at it and say, well, it does look like 4. Actually, it looks like 16 would go into this, right? Because 16 goes into 32. So let's try that. So that equals 7 times the square root of 16 times 20, right? Well, that just equals 7 times the square root of 16 times the square root of 20. 7 times the square root of 16, square root of 16 is 4, so 7 times 4 is 28. So that's 28 times the square root of 20. Now are we done? Well, actually, I think I can factor 20 even more, because 20 is equal to 4 times 5. So I can say this is equal to 28 times the square root of 4 times 5. And the square root of 4 is 2, so that I could just take the 2 out, and that becomes 56 times the square root of 5. Hope that made sense to you. And this is actually a pretty important technique I just did here. Immediately when I look at 320, I don't know what the largest number is that goes into 320. It actually turns out that it's 64. But just looking at the number, I said, well, I know that 4 goes into it, so I could have just pulled out 4 and then said, oh, that's equal to 4 times 80, and then I would have had to work with 80. In this case, I saw 32, and I was like, oh, it looks like 16 goes into it. And I factored out 16 first, and when I took out the square root of 16, I multiplied the outside by 4, and that's how I got the 28. But then I reduced the number on the inside and said, oh, well, that still is divisible by a perfect square. It's still divisible by 4. And then I kept doing it until I was left with essentially a prime number, or a number that couldn't be reduced anymore under the radical. And it actually doesn't have to be prime. So hopefully that gives you a good sense of how to do radical simplification. It's really just an extension of the exponent rules that you've already learned. And hopefully as you do the module, you'll get good at it. Have fun.